Sorry about this. We'll start in a moment. All right, may I have your attention, please? Here's what I'd like to do today. We're going to, really, I have nothing new for you today, so it's kind of like we're doing nothing, because there's nothing new.
No, we're not doing nothing. I don't remember what we did yesterday.
Oh, okay, well, maybe we'll have to do something. I thought we ended with this one yesterday. No?
No.
Yeah, we finished it. We drew the
We did a little
Yes,
sketch
yes,
of a
yes.
cell. I don't know if you had enough time to actually do it. I think I probably just showed you this and said, okay, this is what it looks like. So when you're given a balanced equation, this is not balanced, but when you're given an equation for a redox reaction, I ask you to sketch the cell that would make use of this reaction. You got to figure out what's going to be in the anode and what's going to be in the cathode. Your drawings always look the same. We talked about that yesterday. You have two beakers with a salt bridge in between. Each beaker has a metal plate that's in it, connected by the wire. And then we have to, of course, do the other things that the question asks for. Show what's happening with the salt bridge. What direction are the ions flowing in the salt bridge? Express the chemical equation in line notation. Now, if line notation has been a little bit intimidating to you, hopefully today we're going to do line notation on every example that we do. And I think at the end of the hour you're going to feel a little bit better about it. It is different. But I think the line notation is a little bit simpler than the chemical equation because the line notation has no coefficients. You don't have to balance anything. All you have to do is know what the reactants and products are. And the electrode that goes in. But we'll go over that. So this is what we came up for that reaction. The zinc is oxidizing because the electrons are flowing out of it. So this bar of zinc gets dissolved. Now the whole thing's not going to dissolve, but the zinc does lose mass as the electrons leave it because the zinc metal is becoming zinc ion. So the electrons flow over here to the cathode. Where they come in here, the silver ion migrates over here because you got negative charge coming in, so the silver grabs onto it and becomes silver metal. So we started with a silver plate, and the silver ions are plating onto it. If we measured the mass of the zinc and the silver at the beginning, we would find that the zinc mass goes down as it dissolves. The silver mass goes up because more ions of silver are plating to it. We talked about the line notation on that one. Okay, so let's try one now. I'll have you try one on your own. See if you can sketch this cell. It's going to be similar to the last one that we did. I have 3 examples for you today. With each example, they become a little bit, I wouldn't say harder, but there's more to think about and take into account.
Are we doing this one?
Yeah, try this one.
Oh my god.
It doesn't ask you to do as much as the last one did.
Okay, what is that? Oh, we need to balance it?
The equation, no, it doesn't need to be balanced. Does it ask for the balanced equation? It doesn't.
It's not balanced.
It's okay if it's not.
Is it though?
What did you say? Yeah. No, the projector is kind of running out of juice. The computer guy changed the bulb, I don't know, a month or a couple months ago, but I think the projector is just...
Did she just steal one of the other? You can steal all the history teachers. History could easily be learned on
the what?
How would
Why
we
haven't
lie?
you given you a release mode?
Okay,
You know, like the one like other rooms?
Oh, yeah, like the black ones over there.
This is
I
just
mean,
figured
ours, they call them something else, don't they? They call like these smart ones, like smart actually.
Yeah, smart. Like just all those through house.
I know.
They should give you.
Yeah, well, they think that we're fine.
Because you have such smart students, you don't need.
I guess. You don't need to see the clouds, apparently.
This is a hard one.
No, this is easy. Just like the last one.
Oh,
Whoever is oxidized goes in the anode, and whoever is reduced goes in the cathode.
When do you know where to flip it again? To flip the...
There's no flipping needed yet.
that's when you have to write the equation, right?
Yeah, when you need
Get the total voltage.
when you need an oxidation, all those on the paper are reductions. So if you need an oxidation, you got to find the thing being reduced and flip it. I'll show you when we get there. You know, I guess we do need it in this one. Sorry,
Yeah, that's
Colby.
what I thought.
Yeah, because which one? The aluminum.
Yeah, you flip the aluminum.
The aluminum
No,
is
you flip
no,
the
the aluminum is
magnesium.
reduced. Sorry,
You flip the
It's-
magnesium.
yeah, the magnesium is oxidizing. So find magnesium metal in the products of one of those reductions and turn it around so that it's oxidized. You need the paper that I gave you yesterday. The standard reduction potential table. Yeah.
What is that? So,
Just like take the
Oh, I don't think, oh, no, I'm sorry. Cindy was literally there.
she's an AP tech.
Exactly.
Of course she knows what it is.
Of course she knows. That doesn't help me with that at all.
How? We only care about efficient issues. We don't care. What does- we care about-
Okay, you ready to see the answer?
Not really.
Yes.
Yes.
This is a tough.
Continue.
So we need an electrochemical cell. It's going to look like this. We saw from the equation the magnesium gets oxidized. That's the anode. You got a magnesium bar going in here, and as the electrons flow out of it, because it's oxidation, the magnesium metal loses electrons, becomes magnesium ion. The electrons flow over here, where they come in here. The aluminum ions find the electrons and grab onto them, and that makes aluminum metal. So this is very similar, as I said, to the previous one.
How do you know how many electrons?
I didn't ask you how many electrons for this one, so you don't need it. However, if we look at this, the aluminum, when it reduces, this is gaining 3 electrons. Oops, I just put plus 3 electrons. As it makes that. The magnesium is losing 2 electrons as it makes that. So you would have to balance this thing by getting 6 electrons to be exchanged. So what that's going to take is going to take a 2 there, 3 there, 3 there, and a 2 there. There's a total of 6 electrons. But the question doesn't ask you to calculate that. It doesn't ask you how many electrons are transferred. So you don't need that. It didn't ask you to balance the equation, but that is the balanced ionic equation. So the cell potential. Any problem with the cell potential? We turned the magnesium around and made its cell potential the opposite, or its oxidation potential was the opposite of the reduction potential. So yeah, add those two together and you get 0.71. Do you remember what a positive cell potential means? It means it's a spontaneous reaction. All electrochemical cells have to have a spontaneous reaction.
So if it wasn't and you just did this, would it just not happen?
So if it's not a spontaneous reaction, what would happen is, the electrons would flow the other direction. If it's non-spontaneous in this direction, it'll be spontaneous in that direction. So a current will flow, it'll just give you a negative voltage because the electron's going the other way.
So what would a negative voltage feel like?
No, you can still get shot. It's got the same voltage. Yeah, it would feel exactly the same as the positive voltage, just going the other direction. Yeah, it does. It would feel the same.
So it's spontaneous.
It would still be spontaneous, but in the opposite way. Yep. Okay. Now this one has an extra layer added to it. See what you can do with this, and why and how this one is different from the other.
Polyatomic. The O4. What is this? It's so low to the top.
Not learning on this. They're not learning something.
Regan's a spoiler over here.
That's fine.
Sketch the cell. Yeah, I'm really bad at these drawings. Stop it. Confusing.
There are several exercises right at the beginning of chapter 18 that are assigned that say sketch the cell.
Why do
So-
you keep reminding me?
You don't want to be bothered with homework? No problem.
No, I want to do the homework. It's just that this is so hard. I didn't even get the
Yeah,
answers.
so you need to be platinum because it's a solid.
Kind of
Yep.
figured that
In
out.
one of them, you need to play.
What's the last one? Easy?
Oh, yes.
Whenever you have the MNO4 and the MN, it's like they're both opposite. So then you would need a plan. If it's opposite, why is
What do I
it
do? What do I
opposite?
do as the what do I do in the cathode?
Oh, yeah.
Can you tell who's oxidizing and who's reducing? So in the anode, the iron is changing into iron plus 2. What's your electrode?
The electrode. The electrode is a thing like right there, Fe, right?
Yeah. And in the cathode, where reduction's happening, what's being reduced?
The MN. Like the MN. MN is
The MnO4 is being reduced. Right, it's changing to Mn plus 2.
Do I write MnO4 minus?
So what is the electrode? Yes, you do. What's the electrode that goes into the cathode?
Oh, so it'd be Mn plus 2.
No. Mn plus 2 is not a metal, it's an ion, so it stays dissolved.
Oh, we're supposed to do a Kobe
I'll do
set?
it for a future.
If you're starting with an ion and making an ion, then you got to use platinum.
Platinum just PLE. Shut up, Kobe. Some people aren't good at electrical.
I don't understand this.
You know what I'm
How detailed are these diagrams?
No, that doesn't have to be.
Like, do we have to label all this? Like with the,
Well, it says label the anode and cathode. Yeah. Just do what it tells you to do. I
Is
can't
this
mark
the
you down for
electron
doing
flow?
somebody
Is this
else.
the electron flow always, right?
Well, as long as your anode's on the left, yes.
no, it's like, it's basically, because there's no solid there, you need some
We
solid.
do.
No, it's just that both the MNO4 and MN plus 2 will both be in the solution.
Oh my god, this is so
When you're finding the cell potential, I want to caution you, the magnesium, well, the not the magnesium, the permanganate. There's two permanganates really close to each other. Use the right one. See the other one? It's only like 2 away from the one you're supposed to use.
So you just use the second one.
I think it is the second one. The other one makes MnO2. Yeah, you want the Mn plus the second one.
Why are you calling it that, Kobe? That just sounds so wrong.
Yes, because calling him Ken Daddy is so much better. Wait, no, actually, you call him Ken Dad.
Look, what a trash. Is it lopsided?
I don't know.
Why is this not straight?
Oh man, I tried to make it as straight as I could.
Minus 0.4. So you flip that to 0.
Yeah.
So it's,
I did do this,
what is
What did you get here?
I don't see the Mn.
Right.
What'd you get? I mean, if you just focus on the first 15.
It's still spontaneous, though.
We want to go in the direction show. Here's a challenge for you. In your cathode,
Wait, is it
almost all, maybe all of you will miss something in the cathode.
Salt bridge, except the charges except for the
Okay, we missed something. What is it?
I want you to look for it before I show you.
There's a solid permanganate,
It's where the reduction happens.
Wait, Regan, what did you got as your answer for the overall voltage?
I didn't look at the voltage. How do you say that?
Fe is oxidizing, that's the
What
anode.
did you get?
I'm warning you that you're going to miss something in the cathode.
Yeah, that's AMC. Chemistry. It's American. Math chemistry.
No, in the sketch.
Oh.
And I'm pointing at nothing, I guess. In the sketch of it, yeah. I'm concerned that you're going to miss something. That's why we do this. You know what I'm talking about, Regan?
Oh.
Okay, you ready for it? Are you still working?
Go ahead.
Okay. The thing that I suggested you would miss, in the cathode, you have permanganate reducing to Mn plus 2. You also need hydrogen ions in there.
Oh!
Did you have hydrogen ions?
Why?
Look at your half reaction for the reduction of permanganate.
Oh yeah, I see the plus 5.
It will not reduce without hydrogen ions. This side needs to be acidified. See how the half reaction has hydrogen ion in it? They need to be there.
Where did you want me from?
Yeah, because we use platinum because in the cathode, the reactant is an ion and the product is an ion. Anytime you have an ion making an ion, use platinum. What did you use? Did you use manganese?
I don't even know.
Okay. Yeah, some people sometimes want to use manganese for this one because it is really the element manganese that's getting reduced, positive 7 going down to positive 2. However, that's not right because if you put a manganese bar in here, it's very likely that the manganese will become part of the reaction. Like the Mn plus 2 will probably try to reduce onto the manganese bar. So we need, again, a non-reacting conductor. That's platinum. Because we need this reaction to happen. I don't want manganese part of the solid metallic manganese as part of the reaction. So yeah, no manganese allowed. Yes, Jim? Yeah, you want a non-reactive conductor. So anytime you have an ion making an ion, use platinum. If you don't have a metal product or reactant, then platinum is the choice.
How did you get the voltage?
Okay, so the voltage, our thing that was oxidizing was the iron going to iron plus 2. So listen to this for the cell potential. You find iron in the products. It's down in the bottom right. Turn it around. It's going to be positive 0.44.
1.95.
You see the iron?
Yeah.
And then the permanganate reducing is on the top left. That second one, like we talked
Oh,
about.
that's what I got.
Add the
one number,
0.44
that's
to
why.
it.
Okay, yeah, okay. Makes sense.
Now, how did it go with the line notation?
Pretty hard. Can you explain a little bit?
Yeah, let's go through the line notation. The anode was simple because it's just metallic iron oxidizing to Fe plus 2. So remember what we do to do the line notation. The electrode has to be the first thing, and then we separate physical states with a single line. So it's solid iron going to aqueous iron plus 2, solid line in between. And that's it for the half reaction there. Over here, the half reaction is permanganate reacts with hydrogen to make Mn plus 2. So the reactants are MnO4 and H+, the product is Mn plus 2. These are all, notice, dissolved in water. They're all aqueous. So you don't need a line. You should not have a line separating them.
I thought you said you could though.
No, I did when you have an aqueous thing and a gas. An aqueous, like in the case of hydrogen, you had hydrogen ions making hydrogen gas. That's when you could put a line in between. But when you have all the same physical state, don't separate them with a line. So you do have to put them in order, reactants first and then products. Now, does it matter which goes first, the hydrogen or the permanganate? No. Both of them are reactants. You can put those in the order. Just make sure that the reactants are together first, and then the product comes last.
Wait, so what is that? Are those just the aqueous things?
Yeah.
And then the last
Yeah.
thing you
And then the last thing after the line would be the electrode. You have to say what the electrode is in the line notation. Yeah, Jess?
You show how you got the voltage.
Yeah, let me show you on here. The question was, how do we get the voltage? All right, here it comes. So, if I bring this down, there are two permanganates. I can't see it on the board over there. This is the permanganate that we're using. Now there's two above it is the MnO4, but look at the product, it's MnO2. We're not making MnO2, we're making Mn plus 2. So it's this one where my finger is. You see that?
Yeah.
And then the reduction potential of that is 1.51. That's just for the reduction. Then the oxidation is over here. You have to find iron, neutral iron as a product. Because we're looking for the oxidation, these are all written as reductions. So neutral iron as a product is right here. Now be careful because there's another neutral iron up here. Can you see that or am I off the page? Yeah, see that's a neutral iron, but it's going to plus 3. In the reaction, is iron going to plus 2, so we have to use this one. Which one? There, right there. So that one, we would turn that, the reduction around to make it an oxidation. And the oxidation potential is positive 0.44. So 1.51 for the permanganate, 0.44 for the iron. Add them together. Yep. Anything else about this one?
No.
All right, so you kind of see it?
Yeah.
I got another one. We'll add another layer. This will be the last one, last
How many
example.
layers are you on?
And then what?
And then you're ready for the quiz.
Easy quiz.
Okay, now please don't be one of those that has to write the question out. Well, just write down this number 41B. And it kind of looks like it's intimidating. You have to do all these things. You got 5 lines of instructions. But really, when you start doing these sketches, you do the same thing every time. You put the 2 beakers with the salt bridge in between, the 2 electrodes with a wire. So